This podcast is brought to you by the Environment Institute of the University of Adelaide. For further information, visit our website at www.adelaide.edu.au/environment.
As many of you will be aware, fish move through a variety of habitats. Some of them are estuarine restricted, others you'll find moving from freshwater to marine environments solely for the purpose of breeding. These are typically the diadromous ones. However, the more and more we look at information on the life histories of fish, the more and more we find that it's difficult to categorise any one of them into these basic categories. So this is part of a broader study that's aimed at looking at finding out more information about the key species of fish within the Coorong region. And as I said, I was going to focus on the movement and environmental history component. So what environment do fish actually inhabit at different life stages? If you think of a fish in terms of starting out as a larval organism, moving through to an adult, it's extremely difficult to be able to tag them and then say they've spent, say, X amount of time in estuaries, X amount of time in marine waters. So how do we figure out how much time they may have spent in different habitats as both juveniles and adults? Questions like, do fish need the Murray mouth to be open in order to successfully breed? Questions like, do fish need freshwater flows over the barrages? And how will fish in fact respond to a changing environment? They're all extremely important questions, and this sort of information is needed to get a better understanding of the health of ecosystems and to ensure the long-term sustainability for both social and economic purposes. So the way we've got around being able to figure out the life history of fish throughout their entire life is to focus on something referred to as otolith chemistry. I'm going to go through, first of all, what an otolith is. They're commonly referred to as air bones, and that's air spelt E-A-R. I'm also going to focus a bit on how otolith chemistry actually works. So the otoliths, or the air bones of fish, they're calcium carbonate structures. So they're actually more similar to limestone rock being calcium carbonate than to bone. They're located within the semicircular canals of the head of the fish, and they essentially float within those semicircular canals. There's actually 3 pairs, but the largest pair, the sagittal otoliths, are the ones that are most widely used. And I'm sure many of you are probably familiar with the use of the air bones of fish for age and growth, obtaining age and growth information. Similar to the rings in a tree, we typically use them to determine how old a fish is. In this case, you can see the opaque and translucent bands representing each annulus, and this particular fish would be 3 years old. Now, to use the chemical information within them, the premise behind this technique is that you've got the physical and the chemical environment influencing the rate of elemental uptake into the fish and the subsequent incorporation into the otolith. So, for example, if we have 2 fish, one that spent time in freshwater and one that spent time in saltwater, we'd expect the freshwater one to have much greater concentrations of barium, lower concentrations of strontium by comparison to the fish that spent time in seawater. This is based simply on the amount of those elements available in each of those environments. So if we have a fish that starts off in the estuary, we'd expect this region of the otolith to represent that early life history component. If the fish then moved out to the marine environment, we'd expect the next component to represent the marine environment. If it then moves back in, likewise we'd expect that to represent the estuarine environment. So we can link this information into information about the age of the fish. There's another important point to note. The material, once it's laid down, is not susceptible to resorption. So basically anything that's laid in the early life history part will still be there in the later, if we sample the fish at some point later in the life. So the objectives of this particular work were firstly to characterise the otolith composition and then to estimate the environmental history and movement of fish within the Coorong, and then to feed this information into models that look at the response of key fish to a changing environment. For this talk, I'm going to focus on the first two components. So the work was done in the Coorong. This diagram just illustrates the sampling sites ranging from the estuary, the northern and southern lagoon. And this diagram here just illustrates the water quality along that lagoon in terms of the salinity. We're starting at Lake Alexandrina here, moving along the Coorong, and what you can see is that there's very few sites which we would characterise as being marine. You can see these sites up the north and south lagoon being quite hypersaline, reaching salinities up to 120 parts per thousand. We can also look at the information on the relationship between elements in the water and salinity, and we see the typical logarithmic relationships we'd expect for both strontium and magnesium. However, for barium, we see something that we were completely surprised about. Typically, we'd expect fresh water to decrease as we move into marine waters. But when we looked at samples taken from more hypersaline waters, we can actually see that the amount of barium starts to increase again. And this will, of course, have implications for when we're determining the environmental history of the fish. So the key species we've focused on are listed over here. I'm going to focus on the smallmouth hardyhead, a small atherinid fish that occurs through a huge salinity gradient. It does occur down to freshwater conditions, but it's pretty much the only species of fish we find in the hypersaline reaches of the Coorong. And I'm also going to focus on the Congoli, which is typically viewed as a diadromous fish. So the idea is that it needs to move between the freshwater and the marine waters for breeding, and we can in fact find that over a wide salinity. So what we've done is we've taken the air bones, we've sectioned them, and we've analysed different regions of them or transects across them using what we refer to as a laser ablation inductively coupled plasma mass spectrometer. So this is the laser here, ablates the sample, and then the ions are passed through to the mass spectrometer, this component of the machine. So these are some of the results for hardyheads. We're basically looking at whether we get relationships between the elements and salinity. We get some good relationships for barium that are similar to what we would predict based on the water chemistry. Some variable results for some of the other elements. Likewise, we can look at Congoli. We see similar sorts of relationships for barium and some linear relationships for some of the other elements. Now, rather than focusing on a single element and a single point in the life history, so these were taken from the edge of the fish, which would be representative of when they were collected, we then run a transect across the fish, so this is the early life history through to when the fish was collected, and we can get results like this for a range of elements, and then based on what we know about the water chemistry, use this to make predictions about the environment they've been in. So for example, if we're looking here at a 3-year-old yellow-eye mullet, where we get similar concentrations of both strontium and barium, we might predict they've been in a freshwater environment. Where we've got these two differing, we might expect it's a marine environment. And where we see this sudden increase again in barium coinciding with the increase in strontium, we might predict it's been in a hypersaline environment. However, what we don't just want to be able to look at these transects and look at individual elements. What would be nice is if we could come up with a single profile, so to get a variety of elements and then come up with a single profile for the whole fish and base that on the predicted salinity. So, for example, we could then look and say the fish has spent this much time in fresh water, this much time in brackish or salt water versus hypersaline waters. So what we've done here is we've taken, if you like, a multivariate data set. So we've got here 5 particular elements. We can't view things in 5-dimensional space, so we're trying to draw this down to a single score, which you can see here. And then using multivariate techniques, we've got a score in which we can then look at the score in other fish and throughout their life history and say this is potentially the salinity that they've spent time at. So using that, we're able to analyse a range of species, a range of different individuals, and then come up with transects predicting the salinity history they've been at from birth to when they were captured, and some sort of confidence bands around them here. Now, what I'm going to show you is walk you through some of the data on this graph. The first thing are these solid blue bars, which is the salinity they were collected from, and that's indeed where we'd expect the end of that transect to coincide. So we've got a promising measure to start with. The other key point you should note is that none of these fish have spent any time in fresh water. And the more individuals that we looked at, the less time, or the less, we really didn't find a lot that had been exposed to fresh water for the species that was thought to migrate from fresh water. You'll also see that very few of them, possibly only this fish, have spent any time in brackish water. And at least for the top 2 fish, most of their time has been spent in marine waters. Whereas the bottom 2 fish have also spent relatively little time in marine waters and have in fact predominantly been in more hypersaline waters. So these are just 4 examples of fish collected from different places. If we then move on and have a look at a couple more fish that were collected from the same place, we actually see that these 2 have actually spent some time in fresh water, and also one of them in just brackish and fresh water, versus we can see the time or the life history stage and correlate this back to the age of the fish to see when it moved from the marine waters through the brackish waters to the fresh water. Okay, so just to summarise, basically what we're doing is using the salinity otolith chemistry relationship to predict the environmental history of fish. So the work that I've showed you today focuses on otolith transects for fish where we've collected the specimens relatively recently. The work we're moving on to aims to focus on samples that we've collected from Aboriginal middens and also historical collections where possible. And at least for this particular fish species here, mulloway, people keep, because the otoliths of them are quite large, people kept them as jewels. If anybody's got huge collections of jewels out there, we'd be really interested in being able to analyse some of these to try and get that historical component from the Aboriginal middens around 2,000 years ago through to modern day samples. It's very hard to find anything from the early 1900s, for example. So from this information, we can analyse reasonable numbers of fish and look at common patterns or life history strategies. We can determine what habitats fish are spending time in, whether they're potentially using fish ladders and migrating between freshwater and marine waters. And Following on from this, we can make predictions in terms of different management strategies, whether the closure of the Murray Mouth is likely to impact these fish, whether increased flows over the barrages is likely to be important. Thank you.